Welcome to the video lecture series of solid-state devices. Course code EC301. This is the lecture of junction field effect transistor. Myself, Dr. Shunipa Roy, Assistant Professor. This is Module 4, junction field effect transistor. Junction field effect transistor, this module consists of construction of JFET, field control action and characteristics, recapitulation, pinch of voltage derivation, and numerical problems. This lecture number 8, particularly dedicated for the JFET construction. So, let us go through the history of junction field effect transistor or field effect transistor. In 1945, Shockley had an idea for making a solid-state device out of semiconductors. He reasoned that a strong electrical field could cause the flow of electricity within a nearby semiconductor. And then he tried to build one, but it didn't work. After 3 years, Brattain and Bardeen built the first working transistor. It was germanium-based point contact transistor, which was designed as the junction transistor. Then, in the year of 1960, Bell scientist John Atala developed a new design based on Shockley's original field effect theories. By the late 1960s, manufacturers converted from junction-type integrated circuits to field effect devices. So, field effect devices are those in which current is controlled by the action of an electric field rather than carrier injection. Field effect transistors, the name is that because a weak electrical signal coming in through one electrode creates an electrical field through the rest of the transistor. And the most important thing is the FET is known as unipolar transistor. The term refers to the fact that current is transported by carriers of one polarity only, that is only for majority carriers, whereas in conventional bipolar transistors, current consists of both majority and minority charge carriers. Moving to our next slide. So let us have a look at the types of field effect transistors. Field effect transistors can be classified as JFET, MOSFET. JFET is junction field effect transistor. So JFET can be further classified as N-channel JFET and P-channel JFET. This we will study in this lecture. And then another type is MOSFET, metal oxide semiconductor field effect transistor. Another name is there for this MOSFET, that is IGFET. The full form is insulated gate field effect transistor. So, what are the different types of MOSFET? That is enhancement type MOSFET and depletion type MOSFET. So, enhancement type MOSFET can be further classified as N-channel MOSFET and P-channel MOSFET. Obviously, enhancement type MOSFET can be shortly, we call it as E-MOSFET. Similarly, depletion type MOSFET is another type of MOSFET. We call it shortly as D-MOSFET. There are also two classifications, that is N-channel D-MOSFET and P-channel D-MOSFET. So, we found that there are two types of JFET, that is N-channel JFET and P-channel JFET. there are three terminals in a JFET that is showing in this block diagram, that is source, drain, and middle one, gate. Again, source, drain, and gate. So this is the symbol of N-channel JFET and P-channel JFET. N-channel JFET, you see, in the gate terminal, the arrow is inward, whereas in P-channel JFET, in the gate terminal, the arrow is outward, just like of similar it is to bipolar junction transistor, because in bipolar junction transistor or BJT, we know that if the arrow is inward in emitter terminal, then it is P type, and if the arrow is outward in emitter terminal, then it is N type. But here it is just opposite. Inward arrow signifies that it is N-channel JFET, and outward arrow indicates that it is P-channel JFET. This is gate, this is drain, and this is source. Upper one is always drain terminal and lower one is always source terminal. Now this is the basic construction of JFET. This is N-channel JFET and this is P-channel JFET. For N-channel JFET, what is the difference between N-channel and P-channel? For N-channel JFET, we start with N-type bulk semiconductor, whereas for P-channel JFET, we start with P-type bulk semiconductor. That means we have to purchase N-type silicon and start constructing the N-channel JFET. Similarly, for P-channel JFET, we have to purchase P-type silicon wafer and start constructing the JFET. And you may say that why silicon only? Why not germanium? As you all know that silicon is available in nature. This is abundant in nature. We don't have to purchase silicon. Rather, actually, silicon is made of sand, silica. So the raw material sand, we don't have to purchase. It is available in nature. That's why the fabrication of silicon wafer is cheaper than the germanium. So the total electronic industry has been shifted to silicon rather than germanium. Now this is the basic structure. This is N-channel, P-channel. The upper one is gate terminal. This is source terminal, gate terminal. If you see, you will find that gate is totally covered the material, silicon material, totally covered up. This is actually the cross-sectional view. That's why you will find this type of schematic diagram. So this distance is called channel thickness, and this region is the channel. So what is this yellow region showing? This sky region, sky colored region is actually the metallic contact, but the yellow, the sky color region is actually P type doping. P plus. Here we can see that this is P plus. That is, what does it signify? That is, P region is heavily doped. P plus means P region is heavily doped. But this N channel, this is moderately doped. This is not N plus, this is only N. And this yellow region signifies that this is the depletion region. Why depletion region? As you know, the basic theory of PN junction diode. This is P region, this is N region. So obviously, if there is no applied bias, but there is inbuilt potential and depletion region is there. As you all know, this is the basic theory of our normal PN junction diode. Similarly, here for P channel JFET, the bulk material is P type and N plus. That means the outer region, gate region is N type. That is N plus. That means N region is heavily doped. So here also PN junction diode is formed, and that's why still there is no applied bias, that is zero bias, but there is a discharge region due to recombination of electron and hole pair, and that's why there is a depletion region, as we already studied in our normal p-n junction diode. So this yellow region is nothing but the depletion region. This is the cross-sectional view. So moving to our next slide, the n-channel JFET, this type of n-channel JFET actually made by diffusing p-type impurities in a n-type material substrate. It is a 3-terminal device, one at each end of the channel, one connected to the gate. The device obviously like a PN junction diode, and the one most interesting thing is that source and drain can be interchanged. That is not interchangeable in case of BJT, but this is the advantage of FET, that source and drain can be interchanged. So similarly, for P-type substrate, we start with a P-channel JFET, we start with P-type substrate, and N-type impurity has been diffused. So current flow from source to drain always, whether it is P-type or N-type, and holes injected to source through P-type channel and attracted to drain. So the family of FET devices is, as we already learned in our earlier slide, the junction FET, then MOSFET, obviously depletion mode MOSFET, and enhancement mode MOSFET. So JFET consists of a piece of high resistivity semiconductor material, generally silicon, which constitutes a channel for the majority carrier flow. Conducting semiconductor channel between two ohmic conducts, that is source and drain. Here again the structure is repeating. Now here we can see that this is the top view, this is the gate terminal, and this two small portion is nothing but the metallic portion. This is the metal. This is obviously metal. On top of gate there is a metal layer. Otherwise we can't able to take out the contact from JFET. That's why we have to deposit the metal layer on top of JFET. So here you can see that this is gate terminal, gate region, and on top of that metallic layer is there. Similarly, drain and source metallic layer is there, and where by a very thin wire the output has been taken. So if we apply potential between drain and source or gate to source, whatever, electron starts flowing from source to drain. This region actually showing this portion, and this white region is nothing but the depletion region. This is the channel as shown by the diagram. So the magnitude of this current is controlled by a voltage applied to the gate, which is reverse biased. Remember, in JFET, gate is always reverse biased. The fundamental difference between JFET and BJT devices, when the JFET junction is reverse biased, the gate current is practically zero, whereas the base current of the BJT is always some value greater than zero. This is the advantage of JFET. We don't have to null the offset current. So JFET is basically a high input resistance device, while the BJT is comparatively low input resistance device. And if the channel is doped with a donor impurity, N-type material is formed, and the channel current will consist of electrons only, obviously. There is no concept of minority charge carriers like BJT. And if the channel current is doped with an acceptor impurity, P-type material will be formed, and the channel current will consist of holes. N-channel devices have greater conductivity than P-channel devices, as the mobility of electrons is roughly 2.5 times higher than holes. Thus, N-channel JFETs are approximately twice as efficient conductors compared to P-channel JFET. So, in addition to the channel, the JFET also consists of source and drain. It is showing in this diagram, source and drain. JFET will conduct, actually this JFET, the source and drain is interchangeable as already mentioned. So this is the basic structure. Again, it is showing. This is the depletion region. Now, internal JFET, 3 wires are connected on the device and 1 connected to the substrate. In a sense, the device is like a PN junction diode. So how JFET functions? The gate is connected to the source. See here, gate is connected to the gate and source is shorted. Since the PN junction is reverse biased, if you see that this P region VGS, actually gate is connected to the negative terminal of the battery and gate is of P type, that means the P junction is reverse biased. Little current will flow in the gate connection and the potential gradient established will form a depletion layer as the junction is reverse biased, where almost all the electrons present in the N-type channel will be swept away. The most depleted portion is in the high field between the gate and drain, and the least depleted area is between the gate and the source. Because the flow of current along the channel from the drain to source is really a flow of free electrons from source to drain in the silicon, the magnitude of this current will fall as more silicon becomes depleted of free electrons. Obviously, as the junction is much more reverse biased, number of electrons flow will reduce. That's why the current will reduce. There is a limit to the drain current ID, which increase VDS can rise through the channel. This limiting current is known as IGSS. That means drain to source saturation current when gate shorted to source. So here we can see the IV characteristics of a normal JFET. This current is called IDSS. We will study in later section in detail the IV characteristics or drain characteristics of JFET. This is showing that gate shorted to the source. The initial rise in ID is related to the buildup of the depletion layer as VDS increased. So it was gradually increasing, but after some time, the current increase of current or current increment has been stopped and it is getting saturated. As the curve approaches the level of limiting current, IDSS, when ID begins to be pinched off. This particular point of voltage is called VP, that is pinch off voltage. The physical meaning of this term leads to one definition of pinch off voltage VP, which is the value of VDS at which the maximum IDSS flows. Here we can see that a little bit real life example we can follow. With a steady gate to source voltage of 1 volt. This is 1 volt actually, that is negative, always gate is always negative to source. So there is always 1 volt across the wall of the channel at the source end, this end. Okay. Now drain to source voltage of 1 volt means there will be of 2 volt because the drain is up 1 volt from the source potential and the gate is 1 volt down. So the total potential difference, obviously, this 1 plus 1 minus of minus 1. That means 2 volt. The higher voltage difference at the drain end means that the electron channel is squeezed down a bit more at the end. It is showing in the diagram. A slight change we can observe in the channel depletion layer width. So, if this voltage VDS is increased to 10 volt, what will happen? Actually, the voltage across the channel walls at the drain increases to 11 volt because 10 minus of minus 1, that means 11 volt, but remains just 1 volt at the source end. So, this junction, the drain region, is much more reverse biased than the source region or the source end. As a result, the channel near the drain is squeezed down quite a lot. What we can see clearly in this diagram. See, this region is thicker and this region is thinner. So we can conclude that this region is, upper region is much more reverse biased than the source end. Drain end is much more reverse biased than the source end. So moving to the next slide. So increasing the source drain voltage to 20 volt squeezes down this end of the channel still more. So the reason is clear, I hope. As we increase this voltage, we increase the electric field which drives electrons along the open part of the channel. However, also squeezes down the channel near the drained end. This reduction in the open channel width makes it harder for electrons to pass. See, this region is thicker than this region. So electron is very hard. It is to pass the electron through this region. This is getting very, very narrow. As a result, the drain source current tends to remain constant when we increase the drain to source voltage. So it is very much clear from this diagram and it is very much clear from this figure also. So why do we call this field effect transistor? Why we don't call it as voltage effect transistor? Because we are applying actually voltage. The thing is that though we are applying voltage, but actually the effective parameter that is appearing here, that is field. Actually, field is nothing but the voltage by distance. So the distance is varying. Distance is not fixed in this case. Obviously, channel length or channel distance is not fixed. That's why voltage is constant, but L is varying. That's why E equals to V by L is continuously varying. That's why the field effect transistor, the name has been suggested. So, here we can see that electrons flow from source to drain. If we increase the gate to source voltage, negative voltage, this side is negative and this side is positive. So again, if we go to this figure, see, this is initially 0. Electrons flow from source to drain when we apply a drain source voltage. This is 0. Now it is getting much more negative. Increasing the gate voltage widens the depletion zones, cutting down the flow. So it is very much clear. Again, I am repeating this slide. See, initially the depletion, this channel region was wider. As this voltage is increasing, that is negative voltage is increasing, this channel depletion region width is increasing. That's why channel region width is decreasing. Again, see, a small increase in the drain source voltage increase the current. See what is happening here. The drain to source voltage is increasing. So this will obviously increase the current. If you further increase, what is happening? As this side is positive, this side is negative. This region, drain region, is much more reverse biased than the source region, and the depletion layer width is increasing continuously, and the channel width is decreasing. Again, you can follow. First, VGS is decreasing from 0 volt, and secondly, VDS is increasing from 0 volt or 1 volt, whatever. If you further increase VDS, what is happening? The depletion layer width is getting increased, and this is limiting the current flow. That's why it is getting saturated. So increasing VDS increases the width of the depletion layer that has been just shown in our animation, which penetrate more into channel, and hence channel narrowing towards the drain. The resistance of the N channel RAB therefore increases with VDS. The drain current IDS equals to VDS by RAB, and ID versus VDS exhibits a sublinear behavior. The pinch of voltage Vp is the magnitude reverse bias needed across the P plus N junction to make them just touch at the drain end. Since actual bias voltage across P plus N junction at drain end is VGD, the pinch off occurs whenever VGD equals to minus Vp. So these are the points to be remembered. Source, drain, gate, and channel. What are these? Source through which majority carriers enter the bar, drain through which majority carriers leave the bar. Two internally connected heavily doped regions which form two PN junction through gate, and channel is the majority through which majority carriers pass from source to drain when VDS is applied. So these are the advantages of JFET over BJT. This has got high input impedance, temperature stable than BJT. It is smaller in size and it's unipolar. Can be fabricated with fewer fabrication steps. BJT is bipolar, conduction of both hole and electrons. JFET is unipolar, less noise compared to BJT as it is only consists of single type of carriers usually used as an amplifier and logic switch. Disadvantages, there something is there positive, there may be something negative. So JFET has relatively small gain bandwidth product compared to BJT, and JFET suffers from greater susceptibility to damage and hence requires careful handling. It is costlier than BJT. If there is any question, please feel free to ask me to this email ID. Thank you.